Thank you for having me. I am a solar astrophysicist, or often called a heliophysicist at NASA's Goddard Space Flight Center. I study solar activity, and in particular, I study space weather, mostly space weather from the perspective of what's happening at the sun, but I am interested in what's going on when it interacts with the Earth, or in fact, any of the planets or anything else in the solar system. Um, One of the things that's important for NASA is we have a lot of assets in space. We have things on Mars, we have things that'll soon be on Mars, we have things around lots of planets, all the way to the edge of the heliosphere, which is the domain of influence of the sun's magnetic field. So what I want to do is I'm going to talk about kind of Space Weather 101, give you all an introduction from my perspective. And so a lot of it will just be about what the sun, what kind of activity it produces, how it impacts us. And then I'm going to talk about some of the specific radio emission from the sun, as well as the kinds of impact it has on radio here on Earth, and in particular, how it impacts the ionosphere, which I know is very important for you all. It's just cool for me to, doing a little bit of research, reading about this. I have to admit, I am not, this is not my area of expertise. I do have some friends and relatives who are ham radio operators, but I myself am not. So this is all new to me, and I'm excited to get a bit from your perspective. So start off, the sun that we think about, I think to a large extent, a lot of us take it for granted. I mean, we depend on it. It gives us heat and light. Maybe we'll get lucky and get a nice sunrise or sunset. But in that context, it's kind of boring. I mean, there really isn't a lot going on with it. And when it's not close to the horizon and we're protected by the atmosphere, of course, we don't want to look at it. It's too bright unless you've got the right kind of protective filters on a camera or a telescope or protective glasses. But there is one time when the sun can provide us a unique view of some of the hidden dynamics that are going on in it, and that is during a total solar eclipse. So, this is a unique time when the moon, Earth, and sun are aligned just right. The distance between the distance from the Earth to the moon is also just right, so that the apparent size of the moon and the sun are the same in the sky, and the moon completely blocks the sun out. And when that happens, the bright disk is blocked out, and the much fainter outer atmosphere called the corona, which is somewhere between 100,000 to 1,000,000 times fainter than the solar disk, becomes visible. Now, this is a zoomed in image, but this is real. This is what we can see with our eyes, or if we zoom in with the right kind of filters, we can see with a telescope. You see all this structure. You see all of these loop shapes. We see these fan-like structures coming out. If you look on the right side, you see these pink structures just coming off the limb of the moon. Those are, in fact, parts of the lower solar atmosphere, the chromosphere, which are elevated up high in the corona by the magnetic field of the sun. So this was the first glimpse of what's really going on in the sun. And this is actually part of the beginnings of modern astronomy. Viewing the sun and solar astronomy gave us some of the aspects of modern astronomy. And there are an awful lot of things that we began to discover about the sun's atmosphere, even learning about elements that we had not yet found here on Earth, such as helium. But if we take a different perspective and we put some telescopes in space, that simple disk we see for the sun, if we have the right kind of filters, maybe you would see some sunspots, these dark patches on the sun. But that's really all you would see from optical views of the sun. But if we put a telescope in space, we're above the atmosphere, and now we're able to see wavelengths of light that we normally couldn't see, wavelengths that fortunately don't make it through the atmosphere. We're protected from ultraviolet, extreme ultraviolet, and X-rays and gamma rays. And in this case, if you look at each one of these little slivers, these pies, starting from the pinkish one that's now on the bottom on the right, that's ultraviolet. And as we move around to the other side, we go to the red, for example, which is extreme ultraviolet. That's showing us the chromosphere. That's the part of the sun that we saw during the total solar eclipse. We go a little bit farther now. We're heading towards the right. You start to see that it becomes a little more diffuse looking. You see some loop-like structures, and we're going up into higher and higher energies, shorter and shorter wavelengths, all the way to the far green is near X-ray. And what you can notice here is that there's a lot of difference in the structure and the dynamics of the sun as we look in these different wavelengths. And what they're telling us as we go from the left in the ultraviolet all the way around through extreme ultraviolet to the right, we are seeing different layers of the solar atmosphere. We're seeing higher and higher layers. And also as we go higher and higher up, the temperatures increase. So if we start with the visible sun, we're talking about around 6,000 Kelvin or roughly 10,000 degrees Fahrenheit. As we get to that red chromosphere, we're talking about 40 to 80,000 degrees Fahrenheit. And by the time we get to the near X-ray on the far right, we're looking at temperatures in the corona of several million degrees. So this is one of the great mysteries of solar physics, is why does the sun's atmosphere get hotter as we move from the surface up into the higher parts of the atmosphere into the extended corona? Now, if we pick one of those ultraviolet wavelengths, actually this is a combination of two different ultraviolet wavelengths, you can start to see in this video, this is real data, we're seeing this dynamic sun. You again see those loops, and in fact, I'll show you another image in a second. Those loops are coming from magnetic fields, and I'll explain a little bit about that in a second. But you see that flash of light? That flash is a solar flare. Enough energy is produced in that flash over the entire electromagnetic spectrum from microwave radio all the way up to gamma rays and everything in between. There's enough energy to power the world for about 100,000 years. So it's just a phenomenal amount of energy is released. And at the same time, solar material is thrown out into space by magnetic fields that are pushing it out, and it leaves the sun at velocities of several million miles per hour, billions of tons of that solar atmosphere, and carrying away magnetic field with it. If we look at another one of those wavelengths, this is just one extreme ultraviolet zooming in. Now you're seeing all of those loops from magnetic fields. Now, of course, magnetic fields are invisible. However, the sun itself is a plasma, highly ionized gas. And because of that, it responds to electricity and magnetism. And it is literally highlighting, lighting up the magnetic fields, allowing us to see it. And all of those bright patches now in extreme ultraviolet are in fact where those dark sunspots were in visible light. So you can see the magnetic fields are coming out of those bright patches, out of the sunspots. And that's in fact what sunspots are. They're super concentrations of magnetic fields up to thousands of Gauss. So several thousand times the strength of the Earth's magnetic field. So those magnetic fields extending out into the corona loop back down onto the surface, but some of those magnetic fields actually extend out into space. And what that does is it allows a great deal of that corona to escape. Now, the corona can escape from everywhere, but these open magnetic field lines that are going into interplanetary space are allowing much more easily for the sun's corona, which is now highly energized, to escape into space. And this plasma is carrying magnetic field with it. It's composed primarily of electrons and protons coming from ionized hydrogen, but there are also helium nuclei and even heavier elements. This is what we call the solar wind. And this is streaming out into space through the entire solar system, making up this bubble we call the heliosphere. Here is an image of the solar wind. And you can see while there's sort of a steady stream coming out, there's also a huge amount of structure. There's a lot of dynamic phenomena going on. So it is constant in the sense that it's always there, but it is also very dynamic. And I'll talk shortly about what some of the impacts of that are. So if we go back to talking about the sunspots, okay, these concentrations of intense magnetic field, here we're looking at an extremely active time in the sun. This is 2003, the end of October, beginning of November. Those sunspots are huge. To give you some size, that the smallest ones are close to the size of the Earth, the largest ones are closer to the size of Saturn and Jupiter. So these are just massive, massive structures. And they're quite complicated, quite irregular in their structure. And what that is telling us is that there's a huge amount of potential energy built up in those magnetic fields. And one of the properties of these magnetic fields, these sunspots that we've now been observing for more than 400 years, is that there's a cycle going from little or no sunspots on the sun to very many and large ones like what you're seeing right here, back down to, again, few or none. And we call that period, which is roughly 11 years, the solar cycle, from solar minimum to solar maximum, back down to solar minimum. Here is a look at some of the past solar cycles. The one that you see ending in around 2020 is the end of cycle 24. So we have left solar minimum and we're now moving into the next solar cycle, solar cycle 25. And we'll be reaching solar maximum, that peak, somewhere around 2024, 2025. And we'll start to see a lot more of these sunspots. Now you'll also notice that not only do they vary in length, sometimes a little bit shorter than 11 years, sometimes a little bit longer than 11 years, you'll also see that some of them are much larger in sunspot number than others. The one that we've just left, solar cycle 24, is a relatively low cycle. And in fact, it's the lowest one in almost 100, the smallest one in almost 100 years. And as you go back to cycle 23, 22, and 21, you can see that the cycles are getting larger and larger. And you see back in around the 60s that we're close to the largest cycle. We have predictions based on past cycles for the next cycle, for cycle 25, and the current predictions are that it'll be somewhere around the same size as 24, but possibly a little bit larger. So here is an animation showing you what's happening. So during times of solar minimum, the solar magnetic field is very relaxed. It's in a very simple state, running from pole to pole. And because the sun is not a solid body, because it's a plasma, it rotates differentially. So it's rotating faster at the equator than it is at the poles. The same sort of thing that's happening on gaseous giants like the planets Saturn and Jupiter. And because it's a plasma, the magnetic field is coupled to that plasma. And so as the magnetic field is moving, it's being dragged, and it's being dragged faster at the equator than at the poles. And so what's happening is inside, the magnetic field is getting twisted up. And as it becomes twisted, gaining energy and gaining pressure, it becomes buoyant and is floating towards the visible surface, the part that we saw, what's called the photosphere, the part where the light that we are most used to, visible light, comes from. Here's another animation to show you. You see that the magnetic fields are coming out of the photosphere, where they break through the surface, the visible surface. you see that they are dark. And the reason is those magnetic fields are suppressing heat. So while still fairly hot, the sunspots are maybe 1,000 degrees cooler than the surrounding material, and so they appear dark. And one of the aspects of this is you can see that as the magnetic fields are emerging through the surface, and when they're twisted up with a lot of energy, eventually, if there's enough energy built up, that energy has to be released. And it's released violently, first in the form of, you see this flash of light, that's the solar flare. And then you see the magnetic field is pushing material out into space. And that's that other eruption I was talking about. We call those coronal mass ejections, or because NASA likes to have acronyms and abbreviations, we call them CMEs. And so both the flare and the CME create shock waves. And those shock waves in the solar atmosphere, as well as in interplanetary space, as that CME is plowing through the solar wind, accelerate particles, accelerate electrons, protons, and heavier ions to near relativistic speeds. And so that also creates what we call a particle storm, or a solar energetic particle event. So for the dynamic activity, solar activity, we have these three components. So there's the flare, which is just light. And here I'm emphasizing the X-rays and the EUV. And that, of course, takes 8 minutes. That's the light travel time. The particle shower, in this case, the proton shower, energetic particles, traveling near relativistic speeds, and then close to that and also slower, take somewhere between 15 minutes to an hour to reach Earth. And then the coronal mass ejection, that huge cloud of particles, solar material, and magnetic field, are traveling at a relatively slow several million miles an hour and reach Earth in 1 to 3 days. And I will talk soon about the various kinds of impact those are going to have on Earth. But one of the things I'll highlight here is that coronal mass ejection, when it reaches Earth or another planet that also has a magnetic field, it interacts with that magnetic field and disturbs the magnetic field, and it generates electrical currents higher up in the atmosphere, in the outer ionized atmosphere, the ionosphere, which I'll talk about more. And that does a lot of different things, but one of the things it does is it actually releases energy in the extended part of that magnetic field, and that accelerates particles down to the poles. And that gives us, for example, the northern and southern lights. And I'll talk a little bit more about that in a second. But also, of course, all those particles trapped in the Earth's magnetic field create another structure, the Van Allen radiation belts. And this is a visualization, if we could in fact see those particles, what they would look like as they're spiraling around these magnetic fields, bouncing from pole to pole. And if we look from space, because of all this energy and material that's hitting the magnetic field and interacting with our atmosphere, we get the aurora. So here we're looking from the International Space Station down on the atmosphere. You see that glow on the edge of the Earth. That's called air glow, created from ultraviolet light interacting with the atmosphere. But now you see this dynamic structure here. That's the aurora. We're looking down on the aurora at altitudes above 300 kilometers or so, above the ionosphere. And so the aurora is the first indication of space weather. It's the first thing that we saw in society, that we've seen for thousands of years and have been recorded. But that's just the beginning of space weather. So what I'm going to do now is show you a schematic to just give you a feel for all the different types of impacts that space weather can have on the planet, and things on the planet as well as things we have in space orbiting the planet. So we have really 4 components to space weather. We have the the solar wind component, which is dynamic, but still nothing like the very violent phenomena, the three parts: the solar flare, the coronal mass ejection, and the particle storms. So if we look at the schematic, we have the particles which are impacting the upper atmosphere, which creates a hazardous radiation environment for astronauts in space, in particular astronauts that are outside the protective material of the ISS or some spacecraft. These particles can directly damage spacecraft. They can damage solar cells. They cause solar cells to degrade. Because these are high energy particles traveling through solid state electronics, we can get single event upsets. Bits are flipped. This can be extremely problematic because if you have onboard commands in the software is recorded in solid state electronics, then you're having commands that are being changed as these particles are traveling through it. And so you don't want to have a spacecraft that has a command caused by a particle that tells it to power down or to turn on its thrusters or something like that. And so we not only have to create radiation hard electronics, but we also have to take various mitigations, which would include putting electronics and putting equipment into a safe mode. Now, all of this, the particles, the CME, as well as the flare, are interacting with the upper atmosphere, the ionosphere, creating currents, as well as changing the density of the ionosphere, which is going to disrupt radio propagation, both radio waves through the ionosphere as well as those bouncing off the ionosphere, and something that you all are familiar with, which is the high frequency bands. This is one of the bands that's most directly impacted by space weather. We also have scintillation that occurs as the signals are traveling through these density fluctuations that can cause disruptions with GPS, which is degrading accuracy of GPS. And another aspect is large conductors. So there are electrical currents that are created in the upper atmosphere, and those currents can induce currents both in the ground as well as in large conductors. In particular, those large conductors would be long power lines, especially between substations. Also, that includes pipelines. The pipelines are an issue because currents traveling through pipelines can increase corrosion and degradation. But more importantly, if we have strong enough currents induced in the power systems, they can cause circuits to trip, which is the better of the two situations. But the other one is if we have extended currents flowing through the system, it can heat up transformers and actually knock out the larger transformers, which are extremely expensive and very difficult to replace, especially in a timely fashion. So there have been power outages that have happened. And one of those periods, I showed you these sunspots before, was actually this period, the end of October, beginning of November 2003. This was a period we now call the Halloween storms. So over this 2-week period, we had a huge amount of eruptions from these large sunspot groups. So here you see there are a lot of flashes. You see color changes in the material, and that's actually changes in the material. So that's these coronal mass ejections being thrown out into space. And then eventually you'll see an eruption that's large enough that actually creates snow on the cameras. And that snow is caused by these high energy protons, which are being accelerated. And right there, you saw all that snow. Those are the high energy particles that are impacting the CCD on the camera. We can take a different perspective, zooming out and creating an artificial eclipse with what we call a coronagraph. So now we're going to block out the bright disk. I'm going to overlay this particular image on it so that you can see it, but the sun is basically the visible sun is blocked out, allowing us to see the faint outer corona. You see these puffs of smoke. those are the coronal mass ejections. That bright image on the left is a planet, and then here you see all the snow. This particular wavelength is very susceptible to the high energy particles. So to give you a little overview of what kinds of impact this particular series of solar eruptions had. So more than 20 satellites and spacecraft were impacted. This does not include the military satellites, which we don't have information on because they're classified. This was half of NASA's Earth orbiting fleet. There was a Japanese scientific spacecraft which was lost. There was a severe HF radio blackout, which I will talk a little bit more about shortly, which had a huge impact on commercial airlines. This was also the first time the FAA issued alert for excessive radiation exposure for air travelers and for crew on polar routes, because the magnetic field is weakest at the poles, and this is where the radiation has the biggest impact. There were power failures in Sweden. There were examples where climbers on in the Himalayas experienced problems with their satellite phones going out. The Coast Guard's LoRa navigation system was out. Some of these storms were so large that also, ironically, the radiation monitor on the Mars Odyssey was knocked out permanently, and we were able to measure that part of the Martian atmosphere was escaped into space, and it was permanently lost. You can see here a couple of examples of many of the different observations of aurora. We had aurora down to California. I remember talking to people who saw aurora down to Florida. Definitely a very strong aurora down into Alabama, Virginia. So this is not typically where you see aurora. I will give you an example. These were strong events, but not the strongest events by any means. The strongest event that's in modern history is what we call the Carrington event, which happened in 1859. Now, this is, of course, before we had a lot of the modern technological infrastructure. We didn't have power grids. However, we did have the telegraph system, which was very much impacted across the globe. A lot of the telegraphs were operating without being connected to their power source. Some of them had enough current going through them that their paper ticker tapes that were recording signals would catch on fire, and some of the stations burned down. The aurora were so bright and so strong, they were seen down as far south as Cuba, and there were reports in the West of cowboys waking up in the middle of the night thinking it was dawn because the aurora was so bright. And I'm going to give you one more example of recent space weather, and this is in another solar cycle. This was in solar cycle 23. Sorry, solar cycle 24. The other one was solar cycle 23, and this was in March 2012. So I'm showing you extreme ultraviolet from the Solar Dynamics Observatory. We're zooming in, and you see the flash of light, the solar flare. There are actually two of them, but you can also see the loops in the magnetic field wiggling, and that's actually the material and the shock wave traveling away from the eruption at many millions of miles an hour, and that's real material that's moving around. If we look with a coronagraph, you can see both the CME as well as energetic particles impacting it. And this is just one example of aurora that was seen. So to recap, these are some of the dynamic and constant impacts. So we have sunlight, which is important for creation, especially not only for supporting our life, but also helping to create the ionosphere. Flares, which travel at the speed of light, but they start and they can have time spans that last, minutes to hours. There is also radio noise emission, which is coming from the corona. These are highly energized electrons, which are giving off radiation up to and one of the air, up to many gigahertz. We have the energetic particles, which are taking tens of minutes to several days. Now we also have the coronal mass ejection, which is taking 1 to 4 days, and that at Earth is creating what we call a magnetic storm. That's what happens when the Earth's magnetic field becomes excited and disrupted, and that can last for several days once it reaches us. And then there is the solar wind, and the solar wind usually takes a couple of days to get to us, but it also can have impacts changing the ionosphere, changing the other atmosphere, and also it can create the aurora. So I have a little bit of a review. I'm sure most of you are quite familiar with this, but just to give you some perspective, thinking about the atmosphere, we're living down in down to the troposphere. This is the part we're most familiar with. Of course, the stratosphere. And you get up into the mesosphere. The mesosphere and the mesopause are of interest because most of the meteorites that reach Earth that are ablated and turned into things like sodium and other elements fill this layer of the atmosphere. But that's also when we get to the mesopause and into the thermosphere, or the ionosphere and the magnetosphere being the extended part of the sun's magnetic field, the sort of structure that's around the Earth. That's where the ionosphere begins, and it actually overlaps with the thermosphere and the mesopause. And so, again, sort of I'm probably a review for many of you, but we have the ionosphere, which has the in nighttime has the F region and the E region, but it's energized by UV radiation from the sun, which is causing free electrons to increase. So you have electron density in the ionosphere is going up, and so now we have also the D region, which is often called the D layer. And it's an important absorption region for HF signals. And then the F region separates into the F1 and F2 region. And again, this is where space weather can have a huge impact on HF frequencies. And so I will talk about some examples of how the dynamic phenomena can impact both the transmission and absorption of these particular frequencies. So just one more snapshot just to give you some perspective of here where the aurora sit. Here's where the ISS sits. The aurora is sitting around the E region, 100 kilometers or so. They can go much higher, they can go a little bit lower. And then the ISS is sitting over top of the ionosphere, over the top of the F layers. So what are some of the dynamic emission that can happen from the sun? So the sun can produce several different radio bursts. And these are typically looked at in spectrum. So they actually take strips at different frequencies as a function of time to create these spectrograms. And when you look at these spectrograms and when you have emission from the sun, you see these different types of structures. And they're named type 1 to type 5. In particular, two of the most important ones for us are the type 2 and type 3. The type 3 are due to the solar flares that I was talking about, which are energizing electrons, and the type 2 are due to those coronal mass ejections, which are plowing through the solar wind as they're moving through interplanetary space. I'll show you some real data examples. These are just drawings to just highlight the particular structures that you see. These are real spectrograms. And I'm actually putting these up just because this also gives you a nice view the evolution of data and of instrumentation. So the oldest spacecraft is wind, and then we move up to stereo, and you can see that the resolution has improved somewhat. And then if you actually go up to the top to Parker Solar Probe, then you see significantly increased resolution. And what we're looking at here are the type 2 bursts, which are due to those coronal mass ejections. So what happens when a solar flare occurs? So we know that the ionosphere is created and enhanced by the ultraviolet emission from the sun. It's creating free electrons. So one of the things that we're very interested in and what we measure in order to get density measurements of the ionosphere is what is the total electron content, we call the TEC. And so if you have a flare that's occurring on the side of the sun that's facing the Earth, then whatever part of the Earth that is facing the sun will be experiencing that emission from the flare of not just ultraviolet, intense extreme ultraviolet, but also intense X-rays. And so the side of the Earth that's facing the sun when that flare occurs is going to be lit up by that flare. And what then happens is it creates absorption in the D layer. And this is an example of a moderate size flare, moderate to kind of medium size flare. And you can see the levels of absorption that you have across HF frequencies. And so right at the center is where the peak of the flare is pointing directly at that point, right in the Pacific. Sorry, right off the coast of Africa. But if we look at an extremely large flare, and I'll show you how we measure the size of flares, you can see the difference. So what I'm going to show you is what happens when you have a very large flare. So if you look on the left, you'll see a scale going from A, B, C, M, X, and up. And that's how we label flares. This is just historical, and each one of these is a power of 10. It's a logarithmic scale. So, you know, a C1 flare is 10 times the B1 flare, an M1 flare, 10 times the C1 flare, and so on. And really where we really start to pay attention is by the time we reach an M5 flare. So halfway in up the scale between the M and the X. That's when we start to really notice the absorption that lasts the longest. The stronger the flare, the broader the absorption, but also the longer the absorption is. The longer the atmosphere is heated up, and the density is changed. So if you look at the flare that I've circled here, this is an X 9.3 flare, almost an X10. This was a fairly large flare, by no means the largest, but a pretty strong flare that occurred in 2017. And this is the absorption map. So you can see that it's significantly stronger and has an impact also at the poles. And the other issue here, of course, is the length of time. So the impact is over a much longer time frame. So that's an overview of the kind of basic look at space weather, some of the impacts that the general impacts that space weather can have. And what I'm going to show you, give you a couple of references. So if you want to really follow the sun more closely in space weather, some of you may be familiar, for example, with what we call SWPC, SWPC, which is the Space Weather Prediction Center out of NOAA. So one of the things is the two agencies that really handle space weather in the US are NOAA and NASA. You know, NASA builds most of the spacecraft, including a lot of the ones that NOAA uses for weather prediction. So just like predicting terrestrial weather, NOAA are the official forecasters of space weather at Earth. And once you leave low Earth orbit, once you move away from Earth, that's not NOAA's concern anymore. That really goes to NASA, because not only does NASA concerned because we're putting people into space, eventually sending them back to the moon and at some point to Mars, but we also have all of our assets, all of our spacecraft, as well as our rovers. Soon we'll even have drones on places like Titan, the moon of Saturn. So we have things on multiple bodies in the solar system, as well as traveling through the solar system. So we care a lot about what's happening and what the space weather impact is. To look at the sun directly with some of the best imagery, a good place to go is helioviewer.org. There's solarmonitor.org, which does a little bit broader discussion about what is the particular activity, talking about what sunspots are on the sun at any given time, and then telling you what kind of activity is coming from those sunspots. There's also a nice site that's done, spaceweatherlive.com. And I've been personally gathering information about the sun, really for more general audience. Is really kind of based around thinking about education, called The Sun Today. It's something that I've been putting together with my wife when I have time. I will say I haven't had as much time these days to keep it up to date, so I definitely want to catch up on that. But I do things like show some of the most recent launches related to heliophysics. For example, some of the big ones we had in 2018 was the launch of Parker Solar Probe, which I had showed you some of that really nice radio burst data from. Parker Solar Probe is a mission which is going to the sun's corona. So it will actually be flying through the corona. And so not only will we be understanding the physics at a distance, as well as the problem that when we do measure things in space, we're so far away from the sun that a lot of the information has really washed out. So we'll be flying into the region where both the solar wind is accelerated, as well as where flare and CME activity is produced. But also another mission which we highlighted from 2020 was the Solar Orbiter mission, which is a European Space Agency, or an ESA mission, but it also has NASA support, some NASA instrumentation, and it was launched by NASA on a NASA vehicle from Kennedy. And so it is a complementary mission to Solar Probe. It's not going in as close, and what it is able to do then is actually do imagery of the sun. Parker Solar Probe is going too close to the sun, so literally the cameras just couldn't handle the intensity. But it's also traveling out of the plane of the solar system, so it's going to be looking down on the poles, because of our location in that plane, we can't see the poles of the sun, and therefore we can't measure the magnetic fields at the poles, which is critical for really understanding the structure of the magnetic fields and ultimately what drives space weather. And so Solar Orbiter will be taking an incline up to 34 degrees out of the plane of the solar system to give us that unique perspective. So I'm going to end there. I've put up my email address if anyone is interested and has any more questions, or if you have questions about things that are not in my area of expertise. Certainly, my area is actually not the ionosphere, and I have colleagues that work in that area, and we also have spacecraft that are specifically studying the ionosphere, both from very high, from extremely high orbits, as well as flying almost through the Aurora. Not quite that low down; it's a little too low to orbit, but giving us a much more up close and personal view. And then on Twitter, you can go to @thesuntoday. So I am going to stop there and end my sharing.
This is George, KD2FIU.
Yes.
Go ahead, George.
Yes, thank you. For those of us that have been listening to this great presentation by phone, we don't see your email address if we have questions. Can you give it to us, please?
Absolutely, George. So it's c.alex.young Young at nasa.gov. That's c.alex.young at nasa.gov.
Thanks, Alex.
You're very
Thank
welcome.
you. Very, very good presentation. Thank you.
So,
Alex,
yes.
from what I could gather from your diagram, so the relationship of space weather to other planets is dependent upon the atmosphere and the magnetic fields of those planets?
Correct. So, all of the planets that have an atmosphere have an ionosphere created by the sun, but then not all of them have a magnetosphere if they don't have the magnetic field. And so the impact of the space weather can be very different. So some of the examples that are most important to us are Mars, and Mars does not have a global magnetic field. It did at one time. However, that field stopped many billions of years ago. And then we have, planets like Saturn and Jupiter that actually have very strong magnetic fields. And one of the things about those magnetic fields that's very important is they help keep the long-term integrity of the atmosphere. Part of the reason that Mars's atmosphere has deteriorated over time and is now so thin, it was once much thicker and presumably had a lot of water in it, was because of the magnetic field protecting it. But over time, it literally is eroded away by both the solar wind as well as coronal mass ejections.
As we travel into space with some ambitious programs, what is the effect of this space weather on the communications that we have with the rocket ships that we're sending into space? Particularly, I guess we're using VHF and UHF communications with them.
Yeah. So, there are a couple of impacts there. So we have the cloud, the particle storm, is now going to create, a field of material that the radio waves are going to have to travel through. And of course, another thing is those clouds of material are carrying magnetic field with them. So they do have some temporary disruptions, though those are fairly short term. Actually, I think the bigger impact is twofold. One is the actual impact on the technology, but also we do have some missions that, when they're close to the sun, we're getting a lot of background radio noise from the sun itself when you're very close. And also the other aspect that's difficult is the antennas, once you get really close to the sun, literally get too hot. And so they have to point them away. And so they're very far off in the lobes. The signals are very weak. So part of what the problem is there is the biggest limitation is the telemetry. So the amount of data that we can transmit becomes extremely limited as we start moving away into deep space. So that are some of the biggest issues. This is something that's we're still having to think about and have to deal with. If you go to Mars, you're going to have huge signal delays of minutes and hours, depending on where Mars is. Right now, the other thing we're trying to do is actually look at, obviously this doesn't change the speed of transmission, but we're trying to look at optical transmission, laser communications. That's really more short term. But the other thing that we're thinking about are relay systems. That's another aspect of technology that might be helpful. Can't get past the speed of light, but at least we could potentially help boost the signal and have some relays.
Question?
Yes.
Okay. I understand you have 3 satellites that are at L1, ACE, SOHO, and Discover. Are they all still functioning? And I know they're getting a little older. Is there another one that you have planned coming up that I don't know about?
That's a great question. Yeah, so they are getting older. I mean, SOHO was launched in '95. SOHO was actually the first mission that I worked on out of graduate school. So the only aspect of SOHO that is still in operation are one of the solar wind instruments on SOHO is still operating, as well as the coronagraphs. So those coronagraphs you saw, seeing the coronal mass ejections, that's one of the most critical types of data we need for space weather, because the biggest impact are, and the thing that we can actually plan for, are the coronal mass ejections. The solar flares, once we see it, it's already here. There's not a whole lot you can do. So right now the coronagraphs are still operating. However, they could stop working at any moment, and that would definitely be a huge blind spot. We do have another coronagraph on the stereo spacecraft, which is orbiting and an orbit that's about the same distance as the Earth on the other side of the sun. Discover is relatively new. However, one of the caveats to that is that particular mission was actually the instruments had been refurbished, but the mission itself was actually mothballed at one point. It was
that was Triana, right?
That's right. It was the Gore spacecraft. It was put in a closet, literally, and wrapped up. So it hopefully will continue to last for a while. And it was actually designed to be operational to study to measure the solar wind. ACE, of course, is also as old as SOHO, and so both of those spacecraft, could stop working at any time. And we do have a mission that's being developed for an operational spacecraft. This is actually one of the challenges in the government. So NASA builds spacecraft for science, and they're not designed for operations in this context. And when SOHO and ACE were designed and then eventually launched, was really at the beginning of what we call modern space weather. We didn't even really think much about it. And we knew that there was space weather happening, but we didn't really think about the infrastructure we needed to truly study it and to do things like prediction and whatnot. So this is a big challenge. We, as a matter of fact, we just got a bill in Congress. We're trying to get some national support for the importance of having operational spacecraft. And we're looking at new spacecraft at L1 and also potentially L5, where those are on the lobes out on the side. And that's important because you're sitting at L1, you've got a coronal mass ejection coming from the sun straight to the Earth. It's coming straight at you. And those are the ones you want to know about. Those are the ones that are the hardest to measure, because you're measuring along the line of sight. That's a problem. So ideally, you want to have your spacecraft on either side and look at the CME as it's passing by. So
that would be great. Would you like to see another Ulysses, or do you think the ESA probe is good enough?
I think Solar Orbiter is pretty. It's not going to make the orbits over the poles like Ulysses did.
Right.
However, it's fairly inclined out of the plane, and the instrumentation on that particular spacecraft is both so broad. It's got imagers, it's got magnetic field, remote magnetic field measurements, as well as measuring the fields passing the spacecraft, particles, radio. It's got radio telescopes. So I think the set of data, and as well as the improvements in the instrumentation, really are going to really. I mean, it's already provided some amazing results, and it's not even in its science phase yet.
Very good. Thank you, Alex.
You're welcome.
Alex, question?
Yes, sir.
My name's Andy Bebry. Thank you very much for this presentation. It really was very fascinating. You touched on it briefly before about the Van Allen belt. How are the astronauts protected as they're going through this layer?
That's a great question. There's a couple of ways in which we protect the astronauts. First of all, there are paths that have the minimal radiation and minimal density of the radiation belt. So that's one part. Two, the spacecraft themselves are providing protection. And three, you're traveling through them very fast. So the amount of exposure is extremely short. It's by no means trivial. and this is, this is part of what astronauts in general are familiar with. I mean, the general exposure for an astronaut is 10 or more times the kind of background radiation that you and I experience. But those three factors, knowing the correct path to travel through the minimum amount of them, having protection on the spacecraft, as well as traveling extremely fast through them, means that the exposure is limited.
Is there any long-term research been done on the after effects?
There is a lot of long-term research. There are a lot, there are increased amounts of cancer, and those are especially the case for the lunar astronauts, because the lunar astronauts are the ones that are the most exposed. I mean, at least if you're in low Earth orbit, you still have some protection from a small amount of atmosphere, but you also have magnetic field protection. Once you get to, a high Earth orbit, or, on the way to the moon and beyond, then you're much more exposed. So they have studies of cancer rates. Another area that's really important is there's a lot of eye damage, increased cataracts, and some other aspects that are important. There is also some work and study about neurological degeneration. So there's a lot of issues, and it is by no means trivial to live in space for a certain amount of time. The other aspect that I didn't really talk about are cosmic rays. So if you're familiar, cosmic rays are energetic particles coming from outside the solar system. These are created typically by supernova explosions, okay? These are extremely high energy particles traveling extremely fast. We do have some protection from the heliosphere, but they're there and they're prolific through the whole solar system. The interesting part of it is that when the sun is most active, when we're having these solar eruptions, which we're concerned about, it actually pushes out and decreases cosmic rays. So during solar maximum, we have solar activity to deal with, but the cosmic ray levels are lower. During solar minimum, cosmic ray levels are higher. The difference is cosmic rays are always there. Whereas solar activity, you can see it, we know it's happening, we can make we can take some mitigation to deal with it. But that is, cosmic rays for long-term travel and long-distance travel may in fact be the bigger issue than solar activity, at least for people, not so much for the spacecraft.
Is there a source in black and white that we can review any of these after effects, the long-term effects?
I will find some for you. I actually do have a couple of books that I've downloaded through my NASA library. So those were free to me. However, they may be free everywhere. I don't know, because they're automatically free for me. But I will give you some of the references. And the other thing is I can find some papers, and those might be easier for you to download, but there's definitely some good sources. So you've got my email. Why don't you send me, well, I could send an email just back to Harry, for example, and then just send you guys some of these sources. I'll just gather it, send it to the club, and then you guys can have access to them.
Thank you very much. Appreciate it.
You're welcome. Any more questions for anybody? All right. Well, thank you, gentlemen. I really appreciate your time, and I enjoyed sharing a little bit of NASA science, at least the NASA science that I really love. Also, just to remind you all, we've got a pretty cool event coming up, the Perseverance landing on Mars, 15th and 16th of February. It's going to be as exciting as the Curiosity landing, basically the similar kind of principle. So it'll also have that 7 minutes of terror period, but pretty exciting stuff. So hope that folks can enjoy that. A couple of things that are coming up next end of this year. We've got the launch of James Webb Space Telescope, which is also going to be pretty exciting. We're going to be able to see the youngest stars ever in the universe, as well as even look at atmospheres of exoplanets. So it's going to be pretty exciting stuff. So I will gather some of those resources, Andy. I will send them to Harry's email. And if any of you all have any other questions, or there's any other things that you want to explore, I'm always happy to connect you with other experts across NASA. There's a lot of folks at Goddard. We do everything Earth science, planetary, astrophysics, and heliophysics. So, all right.
Well, thank you very much, Alex. I really
Thanks a lot.
Your presentation was excellent, and maybe at some point we can have you back again in the future.
Hey, I'd love to. I'd love to. And there's always lots of new cool stuff happening. So be happy to do that.
Thank you very much.
Thank you, Alex.
All right.
It was a really great presentation. Enjoyed it
Thanks.
very much.
You guys have a good night.